negative 2x minus 7. So I'm going to go down negative 7. 1, 2, 3, 4, 5, 6, 7. I'm going to start right there, and I'm going to go down negative 2, 1, 2, and over 1. Something like that. Way to make sure that yours is correct, make sure that you have a similar triangle between the origin and the other places that intercepts. Make sure it's similar. This one. I want it into y equals mx plus b form. So, and you may have done something different. You may have done the intercepts. We talked about that last week. X-intercept, y-intercept. May have done that. So you could do that too. Divide by 2. Okay, so 9 over 2 is my intercept, or where I'm going to cross over the b. So that is 4 1/2. So I'm going to go up to 4 1/2. 1, 2, 3, 4 1/2. Negative 5. 1, 2, 3, 4, 5 over 1. Something like so. Y equals 6. So wherever y is 6, that's where I'm going to draw my line. And 1, 2, 3, 4, 5, 6. That's going to be a horizontal line right across where y is 6. And then x is negative 3. 1, 2, 3. All right, there's those. Let's see. Plot the points and that slope of the line passing through the pair.
I was stuck on that. It's okay.
I think it's supposed to be find the slope, but that doesn't even get close. But all right, so I'm going to take the points, and if you remember, last week we had changing y over changing x. This is y2 minus y1 all over x2 minus x1 to find the slope. So this is a point slope formula is what it's called. This here is slope intercept. All right, so y2 is negative 4. Minus y1 is 4. Oh, look at that. I already know my answer. Because this right here is going to give me 0. A 0 divided by a number is going to give me a slope of 0.
Is it? I think negative 4 minus 4 gives you negative 8.
But if you have 4 plus 4, or yeah, you're on the wrong one there.
I wanted to do it easy.
That's the next
I know,
one.
I just tried
Okay.
doing it 8 over 9. I'm like, damn, that's not easy.
All right, negative 8 over negative 9 gives me a slope of 8/9. Now, here is one way I could do that. I could go and plot the point 6, 4. 1, 2, 3, 4, 5, 6, 4. 1, 2, 3, 4 right here. Well, right here. And I could go up 8 over 9, plot another point, because that's my slope. Okay? I also could take this right here, and there's, you remember this one? Y minus y1 equals m times x minus x1. That's the point slope formula. No, it isn't. I've got a point slope.
That one's point slope, the other one is,
This is
the
just
other
slope.
one's just slope formula.
Yep. All right, so y minus y1, which is 4, equals 8/9 times x minus x1, which is 6. All right. Do the distributing there. (48/9). (5 3/9).
This thing is just awful crap.
Yeah. Okay.
8/9 x.
Put the x beside it.
Yeah.
Okay.
Yeah, 8/9 times x.
Add 4 to each side.
Yeah, it would be minus 5.3 repeated.
And then I change it back to a fraction I did. When I add 4 to that, gives me 1 1/3, so that's when I changed it back to a fraction.
Do we have to find the equation of that, and you say to?
No.
I didn't, that's why I asked.
So what? Find the slope, and then all you gotta do is go to 1 and then up and over, up and over. This right here is part of what you have to do on number 19. Because you have a slope that you find, or that you have, a slope that's parallel. Now let's go over that again. Parallel slope is exactly the same as the other slope that you're looking at.
Yeah, and the other slope is flip it over, put a negative on it.
Absolutely. Okay, so in that case, whatever your slope is supposed to be, you put it here and use that point that you have as the x and y, and you should come up with the equation that you have.
Cool.
Okay? Okay, last one. Oh, this is the correct, you're right. Okay, so I have a 2 and a 2 in my y. 2 minus 2 gives me 0. So I know I'm going to have 0 over something. It doesn't matter what it is. A 0 over something gives me a slope of 0. What kind of line do I have?
Horizontal.
Horizontal. Right across the 2. Okay? So it's going to be right here. All right. Well, let's get started tonight. New batteries, so I can go forever tonight.
My brain already hurts. Wrap it up all night.
Amen.
Has it been that bad of a day?
Yeah. I was over 10-6.
Yeah. And you look like you need sleep. All right, so let's talk about some functions. It should be review for everyone because you have all had functions, first of all, and we all talked about it last semester as well. So for a function, the x value is called the domain. The range is the y value. This will also be f of x or function of x. A function is a group of points that do not have duplicate domains, so your x values cannot be the same. Y values can repeat, but the x values cannot. If my x values do repeat or my domains do repeat, that's called a relation. And really, functions are just relationships between the x and the y's. Okay? Vertical line test is on page 141. Vertical line test states that if I drew a vertical line anywhere on that graph, that it would, if it is a function, only cross that graph one time. If it crosses more than one time, it is not a function. It would be a relation. Okay, and you see on page 141, letter A, example 2, letter A, they have drawn that dotted red line over it, and you see that it crosses 2 times. Because it crosses 2 times, it is not a function. That means the x value is the same there. Letter B, it does cross only 1 time, so it is a function. And letter C, might look at, this is a graph of y as a function of x. Even though you are not crossing a line there, it does indicate that it is a function because it doesn't cross over twice, right? To evaluate a function, replace the variables with the number given and find out what the function equals. This is what we would have done in a function table. Okay. I'm not going to make you do function tables. I don't think I even have you do function tables at all this time. Okay. If you
on my website, I think.
They did.
I think so. Like I know
Yeah, there was.
there's some questions on
Because,
there. Like, it says like
because I'm like, oh, these are easy. They're function tables. Then I'm like, some kindergarten. I didn't get them right. I was like, what the
like
hell?
one of them was like x squared plus x minus 6 or something like that.
Yeah, I was looking at
Like,
square inside of
Uh-huh.
radical.
Oh, they're wanting you, I think, to factor it. Hey. So if I want to evaluate this, I'm going to put the -1 in where the x is. So 1 minus -1 squared. -1 squared is 1. -1 times -1. 1 minus 1 gives me 0. Okay, so that's the answer. That's my y on there, if x is -1. And actually, you probably need to put that in ordered pair. If x is -1, y is 0, so -1 comma 0 in the parentheses. Find f of 0, so 0. 1 minus 0 squared. 0 squared is 0. 1 minus 0 gives me 1. How about 2? 1 minus 2 squared. 2 squared is
4
4. 1 minus 4?
negative
-3. And then you, what kind of graph would I have there?
You have
An x squared.
the v1.
Parabola, yep. That's like on 142. On 142 at the top is a parabola. Or even on the bottom of 141. Okay, so there are 4 different ways we can represent a function. This is on page 132, but I do have it all written out, so we can represent it verbally. We can give sentences that are describing how the input is related to the output. Basically, what is the pattern that's going on, you know? Numerically, we can do it by table or list of ordered pairs that matches input and output values. So that is your function table. We can do it graphically by points on a graph in a coordinate plane where horizontal axis represents the input and vertical axis represents the output. So x is your input, y is your output.
this is the graph.
And algebraically, by putting the equations in, putting in an equation with 2 variables, x and y, such as right over here. think of and I've talked to you about this, of it like a well-oiled machine. I want to put that number that I'm using as an input into that machine, and I want that machine to do some wonderful little and then spit something out that is my Y answer. Unfortunately, I'm a female and they didn't come with those noises to make it sound like a robot. Alright, so if I wanted to evaluate this particular function, function of x equals 10 minus 3x squared, I'm going to do that. I'm going to use 2, I'm going to use negative 4, and I'm going to use x minus 1.
Do you want us to evaluate all of this?
Yes, please.
Okay.
Stop where it says finding f of x equals 0, please. Okay, going back to PEMDAS means it says I've got to do my exponents first. So 10 minus 3 times 4, 10 minus 12, and negative 2. So this is 2, negative 2 as an ordered pair. This one, 10 minus 3 times 4, negative 4 times negative 4 is 16. 16 times negative 3 is negative 48. 10 minus 48 is negative 38. Minus 3, I've got to square this. So that's going to make it x squared. This one times this one times 2, so negative 2x. Now I can distribute that 3 into there, okay? So that gives me 3x squared, negative 3x squared, plus 6x minus 3, and all behind 10. Combine like terms here. 7 and 3. There are no other factors of 21, right?
No.
Okay. So it is as factored as it can be.
So then your f of x up there, it would be 4 and negative 38, right? For your order of pair.
Oh, yes. -4, -38.
Is it? Yeah.
And this one, x minus 1 and -3x squared plus 6x plus 7. Okay, next thing, finding the zeros of the function. All you gotta do is set y or f of x equal to 0. So here's my equation. Function of x equals -2x plus 10. When I set the function of x equal to 0, then I just set it equal to 0, so -2x plus 10 equals 0. Move the 10 over like you normally would. So -2x minus 10 equals -10, and then divide by -2, and I get x is 5. So if f of x is 0, x is 5, y is 0. Find the zeros of the function of those two right there. X squared minus 5x plus 6. Set it equal to 0. Find out what your factors are. This one, my factors are, let's see, I want A times C to be equal to 6, and A plus C to be equal to 5. So I have a 6 and a 1. Ooh.
And I got 5 plus minus the square root of 1/2. Do the quadratic formula because I can't remember how to factor.
Okay, you should get the same thing that I do.
No. See, I did that wrong too.
When you're finding a zero for a function,
Mhm.
what are you doing? Like what's that in simple terms? What are you trying to do?
Oh, you're trying to find out what x cannot be?
You're trying to find
Or actually x is, because you're trying to set it equal to 0 and finding out what the x is.
You're trying to find out what the range is, right?
No, what the domain is,
Domain.
because x is your domain. Your range is 0. Because function, when you set it equal to 0, then that's your range. Did you find that to be right, Rebecca?
Yes.
This one happens to be difference of squares. So this one is x is equal to positive or negative 4.
How come?
Because if I put positive 4 here, then it will equal 0. 4 times 4 is 16 minus 16.
No, I'm still on the last one.
Oh, okay.
Yeah. I use the quadratic formula and I didn't get that.
Okay, so let's use the quadratic formula. Quadratic formula is
Negative b plus
negative b plus or minus the square root of
b squared minus 4ac all over 2.
negative b, so 5 plus or minus the square root of negative 5 squared minus 4 times negative 5 times 6 all over 2 times 1. So far, so good?
Yeah.
Okay.
Well, no. Where'd you get your 4 times 5? Isn't it 8? What? I was about to say that's where I messed up.
Nope.
Yeah, that's what I got.
Okay, so 5 plus or minus negative 5 times negative 5 is 25.
Yeah.
Minus 4 times 6, 24, right?
Yeah.
So 5 plus or minus, this is 1 in there. 1
Oh.
all over 2.
I put that all over. I put half of it over 1. And so that's why.
Okay, because this will give me 6 over 2, which will give me 3.
Yeah, it should be.
Or 4 over 2, which will give me 2.
Yeah, that makes sense. I just messed up.
You're perfectly fine. Now's the time to mess up, right?
Yep.
Next week, not so much.
Oh, I forgot there's a test. Oh, shit.
All over 1 and 2?
No, because if I have 5 plus 1, I get 6.
No. Our test is all over chapter 1 and 2.
Yes, ma'am.
How many questions is it?
Whatever website gives it.
Yeah, I don't have any idea.
What?
I can look that up for you tonight, and it may take us more than one time, but it's okay. You'll be okay, I promise.
Right.
All right, so find the value for, all right. Find the value of x for which f of x equals g of x. Okay, so they're going to give you two different equations. Here is the function of x, and here is g of x. And they want you to set them equal to each other. So right here I've set them equal to each other. Here's f of x, here's g of x. And then you just combine like terms, okay? So x squared minus 1 plus 1 equals 3x minus x squared. Add an x squared here. Bring over here.
So you want it equal to 0.
Absolutely.
Okay.
So these are just telling you where your parabola is going to be across your x-axis, right? These zeros.
Yes.
So where do you find out where it crosses the y-axis?
Parabolas will not cross the y-axis unless they're on their side.
Or where's their y-intercept?
Oh, you mean down at the bottom? You would have to do that into a,
You just plug in x or
Conjugate.
0.
Mhm.
You just put, okay.
All right, so a times c has to equal 2, and a plus c has to equal 3. Let's see, this will be 2x This will be plus 2. This will be a minus 3. Okay. Minus 2 plus 3 would give me a plus 1, and then that would give me a negative 3.
So you just
No,
set-
that's wrong.
You just set those values equal to each other. And then combine like terms.
Huh? Can't do it, can I? Plus, nope. Negative b plus or minus the square root of b squared, negative b squared. Is it negative b squared?
That should be squared.
Just b?
Yeah.
Minus 4ac all over 2a. Negative b is 3 plus or minus 9 minus 4 times 2 times 1. All over 2a, which is 2. 3 plus or minus the square root of 9 minus
4 or 2 over 4. Oh, wouldn't that be 8? It would be minus 9.
Okay, so that does equal 1, right?
Yes.
So 4 over 4,
Or 2 over 4.
or 2 over 4.
1.5.
So that's actually going to be a negative 1 because you'll have x minus 1.
Oh, because the next would be positive.
3 plus 1,
4 over
4 over 2 would be positive 2. And 3 minus 1 would be a 2 over 4, so
Well, isn't it 2 times 2? Should be 4 over 4.
4 over 4, which is 1,
Oh, okay.
and then 2 over 4, which is 1/2.
Okay.
So negative 1, set them equal, both of them equal to 0. So here x is negative 1, and this one x is negative 1/2.
What's the example from the book, right?
I don't even know, probably. Why did I not get it right?
You got the answer right, but they factored it out rather than the quadratic formula.
Yeah. I wasn't even factoring.
What page?
135.
What?
135.
Yeah. See, my factoring, I wasn't thinking correctly. All right, so now set, do this one and set them equal to each other. Find the answer, please. X squared plus 6x minus 24.
Is it the very bottom one?
Yes. Okay, that's what you're finished with. If you can do this by factoring, do it by factoring. A times C equals 24. A plus C has to equal 2.
A times C equals 24.
Mm-hmm. Oh, 48.
Or you do 48.
2 times 24?
What is the number to use?
Because if I'm going to factor it, that's what I need to use.
Oh, well,
This one is going to be 6 and 8. Okay. Geez, I'm having trouble factoring tonight.
You see, I didn't do. Oh, that's why, never mind. I didn't carry down my 2.
Oh, I know why. I'm missing a step in there. No. I think that's what the answer is. Oh, I don't, okay.
I got 3 and 4, or 3 and negative 4 the quadratic formula.
Okay,
So yeah, you're 2x minus 6. 3, 0.
should have -4 and -3.
Negative 3? Well, if you plug negative 3 back up into that, you're going to get negative 6 minus 6, which is what I would.
0.
Negative 6 minus 6 is negative 12. Yeah, I got positive 3 with the quadratic formula. See, I can't even remember how to do that, and that was way too complicated, so I just,
On the factory?
yeah. I just-
Don't worry about it, then you do what you have to do, okay? That's why I actually slipped back, well, no, that's not why I actually slipped back into it. I wasn't, for some reason my brain's not really working on factoring tonight. So, either way, it still gives you the right answer, right?
Yeah, yeah.
Sometimes better than me, so. Your boyfriend's about done with his test, his deal, isn't he? One more week?
We learned about, what did we learn about today? I don't know, but I did it
Oh,
for him. We learned about, oh man, now you're gonna make me think. Investment stuff.
probably compound interest. No?
No, she gave him a scenario like he had to invest so much money and then he had to do it either daily, monthly, or yearly.
Is he doing logarithms?
Like it was A equals P times 1 plus the rate over the number
Yeah.
to the NT.
Yeah, how many times they're going to come out?
If he invested $400,000, he'd make good bank.
Oh, absolutely.
I wouldn't have to worry about college the rest of my life.
Absolutely.
With g of x.
As long as you got married,
equals
right?
X squared plus 6x
Or-
minus 24.
We're together
And
forever.
g of x equals 4x minus x squared. Set f of x equal to g of x. X squared plus 6x minus 24 equals 4x minus x squared. Subtract 4x and add x squared to each side. X squared minus 4x plus x squared plus 6x minus 24 equals 0. Combine the like terms. Add the x squared and the x squared, and the negative 4x and the 6x. 2x squared plus 2x minus 24 equals 0. Factor out a 2 from the left side of the equation.
Aw, see,
2
we could have
times the quantity
factored.
x squared plus x minus 12 equals 0. Divide each side by 2. The 2's cancel out on the left side of the equation. X squared plus x minus 12 equals 0. Factor the expression on the left side of the equation. The quantity x plus 4 times the quantity x minus 3 equals 0. You now have two factors multiplied together to equal 0. X plus 4 and x minus 3. When either of these two factors are equal to 0, the product of the quantity x plus 4 times the quantity x minus 3 is equal to 0. So set each factor equal to 0.
Excuse me.
X plus 4 equals 0. Subtract 4 from each side. X equals negative 4. X minus 3 equals 0. Add 3 to each side. X equals 3. So the values of x, where f of x equals g of x, are x equals negative 4 and x equals 3.
All right. Gosh, that would have helped if we would have factored that out, huh? All right, finding the domain. What is your x value? If asked to find the domain, no answer that leads to a division problem where the denominator is 0 is acceptable. That would be undefined, can't do it, right? So when I say find the domain, I'm really looking for just the x value there, okay? So on this one, if I said find the domain or give me what the domain is, my answers are all real numbers except for 2 or negative 2. Because 2, positive 2 will give me 4 minus 4, and negative 2 will also give me 4 minus 4. So 2 and negative 2 cannot be my answers. All other numbers can be an answer there, okay? So that one is all real numbers except 2 and negative 2. 2 and negative 2. Graphing the functions. To graph functions, you should plot the points and connect the dots together. Looking at page 140. Sometimes we have a parabola and such. We cannot just do, well, the easy way that we had it up here. We've got to actually plot some points. The man in the videos, he'll just put an X and a Y like this. If X is this, Y is that. If X is this, Y is that. Okay, so you might see that if you go to look at one of the videos. That's a pretty generic and pretty easy way instead of making a huge function table, okay? Zeros of a function, we talked about that. This setting the function equal to 0 and solving for the variable. Increasing and decreasing functions. I'm just going to touch on a couple of things here. First of all, 143. Well, yep, 143. On 143, example 4, you see what a graph looks like if you have x to the third power. And then if I were going to subtract from that x to the third power, that one next to it, b, is what that looks like. So that would be a decreasing. Recognizing graph behavior, and I just went over that.
I know, like, I have a couple of those, problems on C on
On C.
the C one.
What's going on C? So the function of value t, if t is +1, t is less than 0, 1 or 0, less than equal to t, less than equal to 2.
If you have those, send them to me. You do not even know how to do that. Did you hear that? If you have those, send them to me,
Yeah, that seems just,
because you will not deal with that at all.
it's not even gonna be on the test.
Nope. Should not even be on the test. So we'll talk about some more graph behavior as well as we go through. That's really important. In fact, I drew the graph wrong today, I think, and knew it because I knew graph behavior didn't have, it was Friday, didn't have me drawing the graph like that. What did I do wrong? So I had to sit and wait for it, look, watch it, look at it. 140 to 143, we talked about those. Also 149. 149, you see what happens if you have a square rooted x, the middle one. And what happens if you have a 1 over x? It gives you a reciprocal. Okay, so it's going to look like a mirror image. Over on 148, you know that parabolas are x squareds. And above that, if it's just a single x, you get a line. Next page, the double, step function and greater integer function. You see what that does?
What?
Initially, it starts at 0, 0. See that figure 2.25? Starts at 0, 0.
What are those double brackets?
That is the greatest integer brackets.
What do they mean?
Greatest, that means the greatest next number. Again, that's another one that we're really not, you may touch on it, but
Some of those.
not real. See what it does though if you add 1? Then that initial 1 starts at 1. Okay, so kind of pay attention to that. Any others? On C, on 151, absolute value of x, it's going to make a V. You will have a couple of the greatest integer functions just because you will have a few step functions. Okay, and the step functions are in example 2, which is it uses the greater integer. on 152. On 152, you see some transformations, and all that is a shift in the graph. Here on figure 2.28, you see where the graph initially is x squared, and when it goes x squared plus 2, you see that it moves up 2, okay? That's a no-brainer. However, there are some of them that do the complete opposite of what you would think. For instance, if I look over on the figure 2.29, f of x is x squared. G of x, though, is x minus 2 squared. And it moves over to the positive side, not the negative side.
So y values are pretty. Rearranging my brain right now. Okay, I remember doing, yeah, this manipulating quadratics, we did this before in high school.
Okay.
Yeah.
So it's really important that you kind of pay attention to that box right there, vertical and horizontal shifts, because when you're talking about shifting sideways, it's not always the same as what you normally think. Over here on 153, the shifts for doing the x to the third powers, if you're going up and down, it will totally change kind of the look of the graph. So be aware of that. Those are where you're going to have to plot some points and figure out how they went. Okay? And down, this one, x plus 2 to the third power, you're going to actually drop down 2 because I'm going to go to f of x instead. Oh, no, started with f of x to the third power. So I went to x plus 2 to the third power. So I'm going to raise it 2 places. Actually move it over 2 places and move it up. (154) is just a reflection. If it's a positive x squared, it opens upward for a parabola. If it's a negative x squared, it opens downward. And that's going to be the same thing with all graphs. Okay, if you have a negative x to the third power, it's going to open up the opposite. And then just a few of your square rooted of x over here on 155. And 156 is some transformations. The one thing that I found strange or unique with these, if I multiply it times a number, like 3, such as the first one there, then I get smaller than what it initially was. You see where f of x equals the square, the absolute value of x, and it's wide.
Where?
Then if I multiply 156,
The 2.32.
if I multiply it times 3, it gets smaller. Vice versa, the next one, 2.33. If I start out with just the square, the absolute value of x, and I take it times 1/3, it gets fatter,
Which should be the same as dividing by,
dividing it by 3.
yeah. Okay.
Okay, now that stuff is not necessarily going to be on a test or anything, okay? However, it's important if you're drawing a graph and you can't figure out why you're not getting this right, to know what the graph should look like, okay? And that's the only reason that we even talk about it. Oh, look. Average rate of change. Average rate of change is the exact same equation as we used for the slope formula. This particular one has function of x to the second one minus the function of y, the first one, all over x2 minus x1. This is actually y2 minus y1, because f of x is the same thing as y.
So that's saying on the bottom, so x of 2 minus x of 1, that's saying your value, what you plug into your functions, subtract each other, and those are underneath
What you get as an
well,
answer.
after you plug them
Yep,
in.
yep.
So if your functions were like, oh, that's what you're saying.
Well, I'm gonna take this one right here.
So you would plug like, yeah, like, it's sort of complicated.
It's not as complicated as you think it is right now. That sounds bad, but, all right, average rate of change. I have x to the third power minus 3x. And x, what?
The x squared minus?
Yes. x1 is negative 2. x2 is negative 1.
So you gotta plug those into the
Yep.
same function?
Uh-huh.
They're not two different functions? Oh, no, because this is,
Okay, so what I'm gonna do is I'm gonna take this one and I'm gonna plug it into x first.
yeah.
So negative 2
Four
squared
times-
minus 3 times negative 2. So
plus
4 plus 6,
six,
10. So this one here is negative 2,
1
10.
plus 3,
Okay?
yep.
Next one. Negative 1 squared minus 3 times negative 1. 1 plus 3.
4, so negative 1, 4.
Okay? Now, I'm going to take this.
Yeah.
Okay.
Yeah, you got
So 4 minus 10.
negative 1 minus negative 2 is plus 2. Oh, so whatever, 1, negative 6. Yeah.
So there's my slope. Or, in this case, it's average rate of change, and that actually is, whatever I'm talking about has decreased 6 every year. Okay, so maybe I'm talking about,
So that's a parabola that's going to open downward.
it is,
Okay.
because it's, no, it's going to open upward because it's a positive x squared.
What's the slope?
Slope has nothing to do with that. This right here,
Oh, the value of your x
Yeah.
squared indicates. Okay.
and really, this slope is the exact same thing as the average rate of change. For this instance, maybe you bought a lot of baseball cards, and every year how much it's worth goes down $6. Okay, so try it with 0 and 1, please. 0 and 1. Same formula.
One.
0 and 1. What do I find out?
F of 1 is equal to negative 2, so you have 1, negative 2, 0, 1.
I found, yep. Oh, I messed up, didn't I? Y is 0 minus
Oh, I didn't plug it back into the equation.
Well, I was trying to figure out what you did. I'm like, what did I do wrong?
yeah.
Oh, okay, so I need to plug in 0, 0, and 1, negative 2 back into that.
Absolutely, to the average rate of change. So this one gives me a average rate of change over a period of time of -2. Same situation, bought the baseball cards several years ago, and every year I lose $2 on that investment. Okay,
$2 or 2?
well, right now, $2.
Oh,
Because, well, I don't have it in percentages or anything here.
yeah,
It could be percentage if I was using percentages.
yeah, 2 full or
Yeah. All right.
Example 7, which page?
Go ahead and do the first one there, if you would, please.
That's not a function.
Why?
Huh?
Why?
Because it's got the same Y value.
Okay, that doesn't make it a function. If it has the same one, it can have the same Y value, it cannot have the same X value.
Oh, yeah, yeah.
Typical mistake.
I didn't get that.
1, yeah.
Y change, oh, you didn't get that the Y was the same?
No.
I still have to plug in the formula now, even though I don't know now.
I think we're all brain dead today. Except for maybe Aubrey. She hasn't said enough to know to where I can figure out if she's brain dead yet, though.
Just tired.
Yeah.
I don't know about you guys, but it seems like the weekend, like Friday happens, and it's like, shit, it's Sunday
It's
already.
just a blur.
This week went by really slow to me though. Like
Did
I-
you work?
Yeah.
I worked.
I honestly forgot we had class today until my mom said something. Because I talked to her today. She goes, "Do you have another class?" And I was like, "No."
Yeah.
And she's like, "It's Monday," and I go, "Shit."
Sweetie, I feel the same way. Don't feel like you're the only one, okay? It's just like, Oh, man.
One more class. And I was very upset because this morning, I didn't have work this morning, luckily. So I wasn't gonna wake up until 9. I woke up at 6:30. I was so mad.
I worked 2 to 10 on Saturday, worked 6 to 2 on Sunday, and then came here last night. And I've been up since like 9 o'clock. And I have to work at 10. And I won't get home till around 7. And then I have class at 9:50.
You know what? We have a lot of people doing that.
Brenda is gonna have to wake me up several times during class.
Lots of my students work night shift and come right into class.
See, I would, but I don't want to work 10 to 8 a.m. and come straight to class. So I just do the 5 to 8 a.m.
Yeah.
That's it.
Okay, let's watch what they have to say here.
Find the values of x for which f of x equals g of x, where f of x equals x squared plus 6x minus 24,
Wait a minute.
and g of x equals 4x minus x squared.
Why don't we start with the one that
Set
we...
f of x equal to g of x.
X
X squared plus 6x.
Wait a second. That's what we just looked at.
Example 7. Yeah, we flip. That's not the problem we did.
What? Oh, I know why. Well, I really don't. There.
Would you look at it?
In this problem, we will find the average rates of change of the function f of x equals x squared plus 2x, a, from x sub 1 equals negative 3 to x sub 2 equals negative 2, and b, from x sub 1 equals negative 2 to x sub 2 equals 0. The formula for average rate of change is f of x sub 2 minus f of x sub 1, all divided by x sub 2 minus x sub 1. In part A, x sub 1 equals negative 3 and x sub 2 equals negative 2. When you substitute these values into the formula, you get f of negative 2 minus f of negative 3, all divided by negative 2 minus negative 3. Next, you need to determine the function values for f of negative 2 and f of negative 3. When you substitute a negative 2 into the function for x as shown and simplify, you get 4 minus 4, which equals 0. Therefore, f of negative 2 equals 0. Similarly, when you substitute a negative 3 into the function for x as shown and simplify, you get 9 minus 6, which equals 3. Therefore, f of negative 3 equals 3. You can now substitute a 0 in for f of negative 2 and a 3 in for f of negative 3. In your denominator, negative 2 minus negative 3 simplifies to 1. 0 minus negative 3 gives you negative 3 in your numerator, and negative 3 divided by 1 equals negative 3. Therefore, the average rate of change of f from x sub 1 equals negative 3 to x sub 2 equals negative 2 is negative 3. In part B, you can use the average rate of change formula again, but this time x sub 1 equals negative 2 and x sub 2 equals 0. When you substitute these values into the formula, you get f of 0 minus f of negative 2, all divided by 0 minus negative 2. Next, you need to determine the function values for f of 0 and f of negative 2. When you substitute a 0 into the function for x as shown and simplify, you get 0. Therefore, f of 0 equals 0. You also know that f of negative 2 equals 0 as well from part A. Now going back to your formula, you can substitute a 0 in for f of 0 and a 0 in for f of negative 2. In your denominator, 0 minus negative 2 simplifies to 2. 0 minus 0 just gives you 0 in your numerator, and when you divide 0 by 2, you end up with 0. Therefore, the average rate of change of f from x sub 1 equals negative 2 to x sub 2 equals 0 is 0.
So no change. The other, I wanted to look at the difference there with example 7. You have a 20t to the third over 2 power.
What page is that on?
145, sorry, example 7. And I kind of want to look at the difference there. By chance, did anyone print anything for insurance? Okay. Well, Jill keeps getting these things printed to her printer that's about 40 pages of insurance stuff, and we can't figure out who's doing it. And it just happened again. It happened last week too, and the week before. Just really odd.
Like car insurance?
No health insurance, actually. And it says the city of Hayes, so everyone thought it was mine because my husband works for the city of Hayes. And I obviously have been teaching this whole time, so I haven't been printing anything. We don't know why it's... Evidently somebody wants to print that off pretty badly, but they're not able to find out where it's supposed to be going.
The distance s in feet a moving car is from a stoplight is given by the function s of t equals 20t to 3/2 power, where t is the time in seconds. In this problem, we will find the average speed of the car, a, from t sub 1 equals 0 to t sub 2 equals 1 second, and b, from t sub 1 equals 1 second to t sub 2 equals 4 seconds. In order to find the average speed of the car, you can apply the formula for average rate of change. Therefore, the average speed of the car is given by s of t sub 2 minus s of t sub 1, all divided by t sub 2 minus t sub 1. In part A, t sub 1 equals 0 and t sub 2 equals 1 second. When you substitute these values into the formula, you get s of 1 minus s of 0, all divided by 1 minus 0. Next, you need to determine the function values for s of 1 and s of 0. When you substitute a 1 into the function for t as shown and simplify, you get 20 times 1, which equals 20. Therefore, s of 1 equals 20. Similarly, when you substitute a 0 into the function for t as shown and simplify, you get 20 times 0, which equals 0. Therefore, s of 0 equals 0. Going back to your formula, you can now substitute a 20 in for s of 1 and a 0 in for s of 0. In your denominator, 1 minus 0 simplifies to 1. 20 minus 0 gives you 20 in your numerator, and when you divide 20 by 1, you get 20. Therefore, the average speed of the car from t sub 1 equals 0 to t sub 2 equals 1 second is 20 feet per second. In part B, you can use the formula for average speed of a car again, but this time t sub 1 equals 1 second and t sub 2 equals 4 seconds. When you substitute these values into the formula, you get s of 4 minus s of 1, all divided by 4 minus 1. Next, you need to determine the function values for s of 4 and s of 1. When you substitute a 4 into the function for t as shown and simplify, you get 20 times 8, which equals 160.
How do I get 8? How do I get 8?
You get 8
3 over
because
2 is 1.5 times 4.
so you're taking 4 times 2 because you're taking half of 2. 1 and a half of 4. I have no idea.
2,
So what's 4 raised to the 1.5 power?
that's an exponent?
Yeah.
Oh, I
Is
thought,
it 8?
I have no idea.
I don't know how to do that. I forgot how to do that. Do you take it to the third power and then divide it by 2?
Normally that would be like the square root button
Siri,
with a
what's
3.
4 to the 3 over 2 power?
It is 8.
What?
It is 8.
It is 8. So what Aubrey just did, she put 4, and in her calculator she did the exponent button and put 1.5. And when she did that, she got 8.
Yeah.
Okay? That's why I wanted to show you that problem.
Oh.
So 20 times 8 is 160.
Therefore, s of 4 equals 160. Also, from part A, you know that s of 1 equals 20. Going back to your formula, you can now substitute 160 in for s of 4 and 20 in for s of 1. In your denominator, 4 minus 1 simplifies to 3. 160 minus 20 gives you 140 in your numerator, and 140 divided by 3 is approximately 46 and 7/10. Therefore, the average speed of the car from t sub 1 equals 1 second to t sub 2 equals 4 seconds is approximately 46 and 7/10 feet per second.
Okay, even and odd functions. Actually, I didn't want to do that. Even and odd functions are on page 146. We don't use them very much. However, you will have maybe a couple of questions on your homework. I'm not quite sure. We'll ask you if it's an odd or an even function. Okay?
And on the test.
Yes, you will have one on the test. I know because you will have one on the final.
The function of y equals f of x is even when for each x in the domain of f.
Another designation or classification of functions is in terms of even and odd functions. And you may or may not have talked about this in the past, but we're going to refer to that notion from time to time in the future, so it's worthwhile for us to have some kind of definition or idea of what that means. It goes to the matter of symmetry, it turns out. And we talked about symmetry in an earlier section, and there were 3 types of symmetry, and 2 of those 3 were x-axis symmetry and symmetry about the origin. Remember, the x-axis the y-axis symmetry had to do with a reflection. If the graph reflects in the y-axis, then we have this y-axis symmetry. And for symmetry about the origin, it can be thought of as either a double reflection, a reflection in both axes, or it can be thought of as a 180-degree twist about the origin. And either of those will accomplish that kind of symmetry. Now, symbolically, the y-axis symmetry can be described as f of x is equal to f of negative x. And in this circumstance, if this is true for the function, then the function is said to be even. Now, when we talked about y-axis symmetry earlier, we said, okay, here's how we test for symmetry about the y-axis. Because we have this reflective quality, it turns out that anytime the point xy is on the graph, then negative xy is also on the graph, if we have that reflective quality, you see. All of our horizontal distances can work in either direction. That's basically what it means. And so if we replace x with negative x, we should get an equivalent function. And we start with our equation or our function, and this is really f of x equals x squared minus 3, but I'll write it like this as the working model for our function. And we replace x with negative x, and we get what we started with. And so we say, yes, we have symmetry about the...
I want to stop that real quick. Replace x with 2.
Yeah.
If I have 2 squared minus 3, I get 1. And if I have negative 2 squared minus 3, I still get 1.
Yeah.
That's what he's saying.
So is it, when it's,
That,
you
this
can
one
tell,
was on whatever side, like that.
you could tell on the graph if it's graphed and there's like a parabola, or if it's a x cubed. If they both end up pointing the same way, they're even. If they're pointing in different directions, they're odd,
Okay?
right? Or
Yes, that, according to the figure here, 2.22,
uh-huh.
if they are pointing in a different direction, it's odd. If they're pointing the same, it's even.
So if it was x to the 4th power, it would go down, and up again like a W?
X to the 4th power usually repeats x squared.
Oh, it just looks like a quadrant.
Yeah.
y-axis. But I want you to understand that in doing this, what are we writing? What is this? Well, this is f of negative x. You see, this is consistent with the symbolism or the notation that we have here. At any rate, this kind of function is said to be even. An odd function is a function that is symmetric about the origin. And the notation for that and the check for it can be illustrated like this. That given a function f, if the negative of f of x is equal to f of negative x, then we have this symmetry about the origin, and the function is said to be odd. Now, here's an example of the situation. I'm going to show the example in the way that we talked about symmetry about the origin before. And that kind of symmetry involved a double replacement. We said that if the point xy is on the graph, then the point negative x, negative y is also on the graph. And so that comes from that double folding idea. But at any rate, if this is our equation, then we replace y with negative y and x with negative x and see if we can manipulate this to the original position. And it turns out that the cube root of negative x is the same as the negative of the cube root of x. And multiplying by or dividing by negative 1 on both sides gives us the equation that we started with. Okay, so that is the way that we would have verified symmetry about the origin for this equation in the past. Now we can use this notation to perform the same task. That is, if we have this, then, you know, in the function notation, we would have f of x as the cube root of x. Okay, so we would have this. Now, what does it mean to write the negative of f of x? Well, the negative of f of x would be the negative of this. And what is f of negative x? Well, it means in the f function replace x with negative x, so we would have this. Now, are these two equal? Go like this. Yes, they are the same. They are equivalent to one another, and therefore we have this kind of symmetry. Incidentally, to see that these two are indeed equivalent, let x be replaced with, let's say, 8. So this would be the cube root of 8. The negative of the cube root of 8. The cube root of 8 is 2. So this would be negative 2. If x is 8, then this would be -8. The cube root of -8, -2, -2, -2. So these are indeed equal to one another.
I think it gets a little easier once you put a number in there, because otherwise you're just, what am I looking at?
Theoretical problems.
Yeah, absolutely.
Something you can touch.
Parent functions are start on 147. A parent function is a function that you start out with, and a constant one will be going horizontal and or vertical, where your x or y does not change. Your identity one, I'm sorry, I guess your identity one, they're saying, is where is 2.24, the line. Where your slope is 1, and so you're just increasing by 1 over 1. Squaring a function, we kind of talked about. There's some stuff, cubes, square roots, reciprocal functions, step and piecewise. Then more parent functions on 151. Oh, squaring the function is down below on 148. So x squareds. Sorry, cubics, square roots, reciprocals. We kind of talked about those a little bit earlier. Piece wise. Every once in a while I'll see one of those on homework, but not often, to be honest with you. There are those on your test though, so. Transformations over on 152, we have talked about some of those as well. The shifting up and shifting across and what that looks like. Reflecting graphs, which is on 155, 154, 155, where they take and they will reflect along the x or the y axis. Usually, sometimes it might even be the origin. I do like to watch this one on rigid transformations here.
Where's the blood drive from?
Over across the street, where we used to have our map.
Yeah. When
It-
is it?
It's right as you walk in the door. You just go straight. The CNA lab,
What time?
12 to 6.
noon to 6.
I'm out.
Huh?
I'm out. I can't do it.
Wow.
I'm sick. All those night on.
Yeah, just boil the blood. So they do bad water.
No, if you're sick, they won't take it as long as it's not 2 weeks.
I'm just kidding. I'll go under an afternoon class. Yeah.
Do we get extra credit if we donate?
Skips do. Skips gives his students extra credit. Actually, most generally, he tells them you go down there at such and such a time, and you can be done when you're finished.
I'm just gonna call him Mark and tell him I'm passed out and send me home. I always do that. I get made up fun of being a pussy because I get a couple days off. So.
Briefly, and they're called non-rigid transformations because they actually change the form, the shape of the graph somewhat. They make the graph look, well, a little bit fatter or a little bit thinner. That's the idea. Now I can show those well, rather than come over here, let's come over here. I want to consider those in just a moment, because they'll be the result of what I talk about over here. Consider the idea of a y which is, let's say 1/3 x squared. Now 1/3 x squared. And this is equivalent to saying 1/3 f of x. But what does that mean? That these vertical distances are 1/3 those vertical distances. For every x value, these y values are going to be 1/3 as high as those y values. You see, that's the idea. So, gee, I have a pretty complicated looking graph up here, but I need to put in this graph, the graph of this one if I can. I'm going to take this rascal out and see if I can create some room. All right, let's see if we can do this right on top of this. Now, I'm looking at this graph, and I'm thinking all the vertical distances described here are just 1/3 as high as those. So, for an x of 1, we had a vertical distance of 1. You see on the basic graph. But now for this one, 1/3 x squared, it's 1/3 of that. It's 1/3 as high. And for an x of 2, we had an f of x of 4. You see on the basic graph. 1/3 of that is about right here. And then for an x of 3, we went up to 9. 1/3 of that is 3. You see what's happening? This graph is sort of fattening out because of this coefficient of 1/3. Same thing will happen over on the other side. So we'll get a graph that kind of looks like this. You see, it just kind of broadens it out a little bit. If it was 1/10, it would really lay down pretty much like that. Okay, so if we multiply by a coefficient that is between 0 and 1, it will cause this fattening idea. Actually, if we multiply by a coefficient that is between -1 and 1, you see it's the positive or negative ordinary everyday household fraction as a coefficient times the function. So it causes it to kind of lay down. Now if it's negative, it'll cause the reflection to happen, but it'll still widen out as well. Okay, now what happens if the number turns out to be, let's say 4x squared? Well, a coefficient like 4 will just make all of the x values associated with y equals x squared, it'll make every one of them 4 times as high. You see, just the vertical distances are 4 times as high. So when I talk about an x of 1 going to 1 in the basic graph, the x of 1 in the graph of this rascal will go up 1, 2, 3, 4. You see, and -1 will do the same thing. So that graph will kind of look like this. It look really thin. So it'll cause the graph to kind of thin out like this when you multiply by something that is greater than 1 or less than -1. All right. Non-rigid.
Now that explains why it does that. I like his board. I wish I had that on my board. Okay, combinations and functions. This looks very complicated. It's really not, though. So combinations and functions, that's on page 147, I think. I just closed my stupid book. Nope, long ways from there. 157. In the box, it indicates that if you want the sum, you're just going to add the two together. If you want the difference, you're going to subtract them. If you want the product, you're going to multiply them, and if you want the quotient, you divide them. Okay, so if I have f of x is 2x minus 3, and I want to add g of x, then I'm going to add this to it, x squared minus 1. Combine like terms, do your thing.
So you would have x squared.
X squared plus 2x
Plus 2x
minus 4.
Okay, minus 4. Okay. You're just combining like terms, you're not foiling.
Nope.
Simple enough. That's
Subtracting, first you got to distribute that negative into there. And then do the same thing as you did when you were adding. multiplying, you just multiply the two, kind of like when we did complex numbers, and we multiplied them. Or you're foiling there, and dividing, same thing. Inverse of a function is the opposite of a function. If I have the positive version, I want the negative version, so on and so forth. There's some other criteria there, though.
Well, the idea of inverse function is this. That if we take a function f of x and we can write it as y equals this expression, where we want to find the inverse, and I'm talking about generating the function which is the inverse of f, there are actually two techniques that are possible. One is to just replace x with y and y with x here. When we inverse, we just exchange the role of x and y. And so we can exchange roles right here, and then we can solve this for y. And that's the way I'm doing it here. The other way is to just take this form and solve this form for x, and then exchange the x and y. But it really doesn't make any difference. Okay, here we go. I'm solving this for y, so I'll square on both sides. I have x squared is 2y minus 3. Adding 3 on both sides, I get x squared plus 3, and then divide by 2, and I get this. So I have y equals this expression. Now, the notation for this new relationship between x and y is that it's the inverse function of f, or it's f inverse of x. And the notation is f inverse of x like this. The little negative 1 here is not an exponent, it's the notation for inverse function. So the inverse function of x is this. Now, what you ought to notice about this is that functions and inverses have inverse operations involved in them. Look at what we started with here. We have 2 times x. We're subtracting 3, and we're square rooting. Well, the inverse operations then in the inverse function should be, let's see, the inverse of square rooting is squaring. The inverse of multiplying by 2 would be dividing by 2. The inverse of subtracting 3 would be adding 3. And we have all of those ideas down here. We have squaring, we have adding 3, we have dividing by 2. You see, so we're just exchanging operations. We're taking operations and we're writing inverse operations basically with the inverse function. Now, what's really intriguing about this, and there are a lot of things, but what's kind of neat is that all of the roles that are played by x and y are just reversed when you compare functions with their inverses. And that includes things like domain and range. The domain of this function, let's see, the acceptable replacements for x, the replacements for x that make sense. Let's see, we're taking square root, and if we're talking about real numbers, the real number system here that makes sense for us, and we want values of x that will cause the radicand to be positive or 0. So x has to take on values that are 1.5 or larger. So the domain then would be x is greater than or equal to 1.5, or in interval notation, it's the interval from 1.5 to infinity. And the range, let's see, the range means the y values that come out of these calculations. Turns out that when we take the square root of numbers, we always get positive numbers or 0. So y is greater than or equal to 0, or in interval notation 0 to infinity. Now the idea when we go to the inverse function is that the roles of domain and range are simply reversed. That is, the domain of this inverse function will be the same as the range of the function itself. So the domain will be 0 to infinity. The range will be the same as the domain of the original function. So the range of the inverse is 1.5 to infinity. Interesting idea. Now, let's see how those ideas manifest themselves graphically. Well, if we were constructing the graph sort of by hand using a point plotting method, then we would take our function f and probably write it in the form of y equals the expression, and then we would generate points to plot. We do that just by popping in values of x and figuring out values of y. Well, 3 values that could go in here are these 3. And I just chose values that turned out to have integer components here for both x and y. Now, when you perform the same kind of operation over here for the inverse function, you find out that you get exactly the same values but in reverse. All right, maybe I should say in inverse. That is, 3 points that happen to appear on this graph are the points 1, 2, 3, 6, 5, 14. Now notice here that the column of x values is the same as the column of y values over here. And the y's here are the same as the x's here. Another situation of this role of x's and y's being exchanged when we are talking about functions and their inverses. When we plot the points here, and look at the graphs, here's the graph of f, and here's the graph of f inverse. Now, notice points like, for example, here's the point, let's see, 1, 2, 3, 4, 5, 6. This is the point 6, 3. And this is the point 3, 6. So if 6, 3 is on the graph of the function, then 3, 6 will be on the graph of its inverse, as we saw from the tables of values. We notice that there is a reflection idea, that the function in its inverse will appear to reflect in the y equals x line. This is the y equals x line. And there's really no mystery in that, in why that happens. There's a perfectly good reason why that reflection occurs. And let me illustrate that this way. If this is our coordinate plane, on the x-axis, the positive values lie out to the right and the negative values to the left, and on the y-axis, the positive values are up and the negative values are down. Okay, what we'd like to do in this exchange process when we create or generate inverse functions is that we want to exchange positive x values for positive y values. You see, we're exchanging all the x's and y's. So positive x's become positive y's, negative x's become negative y's, and vice versa. So it's a complete exchange of those two. Now, graphically, if we're going to exchange sort of positive for positives and negatives for negatives, you see, can we, for example, just take the x-axis and move it up here to the y-axis? Can we just twist it around? Well, that would exchange these positive x's, and they would become positive y values. But in doing that, in twisting the whole coordinate plane around like this, these positive y values would become negative x values. You see, in that kind of rotation process. So what has to happen is this. We have to have a situation where we twist like this, you see. And in twisting like this for the graphs of the inverse functions, the positive x's become positive y's, and I'm twisting around these positive y values, twist around the back side, you see, you can think of it like that, and become positive x's. And the same idea with the y values. So no wonder we get that kind of reflection in the y-axis, in the y equals x line. Now, it's a reflection. It kind of looks like from the graphs that we have here that all of one graph will lie on one side of that y equals x line, and all of the other graph will lie on the other side. That's really not the case. The graph of one can certainly go through this imaginary line, and all that would happen is that we would have a twisting of that entire graph around this kind of rotation point, if you want to think of it like that. Okay, those are all characteristics that I'm sure you've seen before. The acid test to...
Well, maybe not. Okay, so that's inverse functions. And that leads me to the end. Now that you're all tired. And you're sucking on a bottle.
Better this one or the...
What?
Better this one than the alcoholic one.
Depends on how you think about it. But yes, for you, definitely.
Yeah.
Now, you know you've got an assignment due on Sunday. I'm only assuming that it hasn't been so tough yet, because I've only got one request for help. That doesn't mean anything. But I know that you were introduced to a lot of new stuff. Okay? So if you need assistance, please let me know. Also, I'm here for about an hour left, so if you are wanting to stick around, stick around.